So, dear students, welcome to the lecture number 9, and today I'll speak about tracking. Before I continue, I would like to tell you an inspirational quotation. Victor Hugo, a French writer, said that let us study things that are no more. It's necessary to understand them, if only to avoid them. So today the learning objectives are given as here. First, you will understand three categories of tracking. Second, you will study different body parts as well as environment, and the ways how we track them. And we will watch several tutorials today, and then we will conclude, and you will get a small homework to install Blender at home and start working on your labs. So the language note is shown here. So I would like to clarify some important terminology. So the first word is tracking, means to capture, to catch, to trace. Eye tracking means the marketing activity of watching the movement of people's eyes when they're looking at an advertisement in order to find out what attracts their attention. DRF stands for the degree of freedom. As you know, different objects may have different degrees of freedom. Mapping means calibrating, calculating, and checking. So first of all, let's watch a short tutorial. So this tutorial will explain you how motion capture works in movies and animations. Please
Hey
attention.
everyone, today I'm going to be talking about motion capture, and I'm going to be saying how it works and how it's helped out in a lot of films and video games. But before I say how motion capture works, we need to know what exactly motion capture is. So I'm going to be talking about both those things in this video. So you're probably thinking, yeah, I already know what motion capture is, but it isn't necessarily all that you think it is. It's only the capture of bodily motion. It's not actually the capture of the face or eyes or anything like that, just bodily motion. And there's two overarching types of motion capture, with the first being optical and the second being non-optical. So optical is based around cameras that tracks some sort of tracker's movement and translates that into data that a computer can use. And non-optical still brings in data, but it does it from mechanical movement or inertia movement or something like that, something that doesn't rely on cameras. Most of the time you're probably going to be seeing optical motion tracking, but there are some non-optical motion trackers out there. With a good example of this being the Xsense suit, which uses accelerometers as well as gyroscopes to track the user's motion and translates that into data that again a computer can use. And in case you didn't know, accelerometers measure the acceleration, tilt and vibration, and gyroscopes measure orientation and how fast the motion is happening in a 3D space. But yeah, optical is a lot more common, and it comes under three types itself. There's active and there's passive, and there's also markerless, which isn't necessarily classed as a separate category, but although it is pretty different to active and passive. So passive is the one that you're probably used to seeing. It uses these kind of reflective spheres that are placed strategically along a suit that a person wears. And how this works is that there's infrared lights all around the cameras, and this infrared light shoots off, hits the reflective spheres and bounces back, and the time it takes between leaving the camera to coming back to the camera is used to animate a virtual actor. Active is pretty similar to passive, although the difference is that active makes the light itself, and it sends that light to the cameras without the cameras having to send light to it first. So this is used in outdoor scenes where light changes and may not be that good at the time. And active systems are also pretty good too, because the lighting on the suits can be adjusted by bringing them up and down in brightness, and they can also be switched off if they're not actually needed. And then there's markerless systems, which don't use any sort of tracking devices. Instead, it relies on finding a specific part of the body or seeing specific clothing, and it uses that to track instead. So this is a lot more common for consumers in Connect and on Snapchat even and Instagram. Those sorts of things are markerless tracking because there's no markers on your face or anything like that. But motion capture isn't usually the only thing that's used in movies nowadays. It's usually just used in pre-visualization and for video games. But when it comes to modern movies, they usually use performance capture, which actually includes motion capture, but it also adds on the motion capturing of the face, as well as eye movements and things like that, and it also captures voice at the same time too. So the motion capture of facial features is done by a camera that's right in front of the actor's face pretty much the whole time. So if you look at behind the scenes videos and you see that kind of camera in front of the face, that's what it's doing. The results of that performance capture could be seen in real time by the director. So if something didn't look good on the virtual actor, they could redo it or just make whatever changes are needed. Although this virtual character was only rough, it wasn't the final character by any stretch of the imagination. There still had to be lighting added to it. The animation had to be further refined, so it's not a final product or anything, but it is something that the director can look at and see if it's coming out good or not. And yep, that's how motion capture works, as well as performance capture. So if you like this video and you want to see more...
So dear students, from this video you understood probably what and how motion capture works in movies. So first of all, I would like to tell you that keeping track of moving bodies in the physical world is an important part of any VR system. So tracking was one of the biggest obstacles to overcome to bring VR headsets into computer electronics. As you know, first VR headsets, which became very popular, they were actually built up in the beginning of 90s, and of course they were not excellent, but still some people and scientists, they used them. So highly accurate tracking methods have been mostly enabled by spatial commodity hardware components such as inertial measurement units, which are actually used for stabilization. As you know, many nowadays cameras, they have these units which are integrated inside the camera. So moreover, cameras also were used, and the size and the cost due to development of smartphone industry was also decreased. So here on the next slide, I would like to classify all tracking into three categories. So the first one is tracking of users' sense organs. Here we can mention about some sense organs like sight and hear. So eyes and ears are having degrees of freedoms that are controlled by human bodies, of course. As you know, eye and ears, they also have 6 degrees of freedom. So if artificial stimuli are attached to these organs, so then the position and orientation of the organ needs and can to be tracked. So most of the focus, of course, is on the head tracking, which is sufficient for visual and oral components of VR systems. However, the visual system may further require eye tracking if the rendering and display technology requires compensating for the eye movements. So as you know, many nowadays modern VR headsets, they integrate actually eye trackers into their system. So you can find eye tracking device inside VR headset. So this is very important, especially when you play some games and if you want to control so what happens around you with your eyes only. So the second category is related to the other body parts. So if the user would like to see a compelling representation of his body in the virtual world, then its motion needs to be tracked so that it can be reproduced in the matched zone. Perhaps facial expressions or hand gestures are needed for interaction. Although perfect matching is ideal for tracking sense organs, it's not required for tracking other parts. Here, I also need to mention that small movements in the real world could convert into larger virtual world motions so that the user applies less energy. So here we can track some of the body parts as mentioned before, like facial expressions and hand gestures. Also, we can track whole human body in general. As you know, human body consists of some bones and joints. So bones can be also called links, and of course they will be connected with joints. So please have a look on this slide. So here I would like to raise a question: how to track human hair? So as you know, there are many hair on a human head, so we cannot even count them. So tracking hair becomes very complex. Some people may have long hair, some people can have short hair. So instead we try to use some surfaces as shown here, so which will representing hair in general. So the last category of tracking is related to the environment. So as you know, physical objects in the real world which surrounds the user may need to be tracked. So that might be objects like a river, a stream of water, or a sea, or some tree with leaves on it, or flowers. Imagine that a user is about to hit a wall or trip over a toddler. And many other examples can be also mentioned here. So in some VR applications, the tracked physical objects may be matched into VR so that the user will receive touch feedback while he interacts with them. So in some other applications, such as Telepresence, a larger part of the physical world could be brought into virtual world through live capture. So on the next slide, I would like to show you how and what kind of objects from the natural world can be tracked. So one of them is the leaves or the flowers of a tree. Here is sakura, or dropping water stream also can be tracked. So let's go to the next page here. The next video is presenting robot which is called Telepresence robot. Please enjoy watching.
Hello, I'm Tom Simonite, computing editor with Technology Review. This telepresence robot from Daegu Communications is one of a handful hoping to find favour with office workers looking for an alternative to travel. And it certainly beats phone or video calls. While sat at my desk in San Francisco, I can roam corridors in Cambridge, Massachusetts, seeking out people in their offices, attending meetings, and joining in with gossip in the kitchen. But replacing a person with a machine is not always straightforward. In our January issue, I have to take a look at the social side of becoming and working with a robot.
Controlling one of these telepresence robots is like using a video chat program with a few extra controls to steer yourself around. You can do most of the things that you would do in person. For example, stopping to talk with people you meet.
The Dominican Republic was great, Tom. They're trying to get a 2-year-old baby down to the Dominican Republic was difficult.
Oh, alright. Well, I'm sure he liked it when you got there.
Yeah.
Or having a conversation as you walk down a corridor alongside someone. Because you can get a feel for the space around you and watch people's body language, those conversations are much like those you would have face to face. I got much more out of our morning meeting as a robot than I would dialing in on the phone as usual, and the people there could talk to the machine as if it was me. But the extra engagement a robot provides makes any problems extra frustrating.
So we didn't catch any of that, but I realised it's just that she's
Trying to keep pace with a meeting when a bad connection is causing your robot body to misbehave, making your colleagues laugh, is a stressful experience. Some problems, like my difficulty steering because of the limited camera view, have technical fixes. For example, telepresence robots are appearing that use obstacle recognition to prevent crashes. Other glitches will go away with practice. Academic research shows that machines that try to act in place of people often encourage high expectations that they cannot always meet. Ultimately, a telepresence robot will always be slightly less slick and less capable than you would be in the same situation. If these robots become more common in the workplace, we'll have to learn a new set of social skills reserved for our colleagues that are machines rather than people.
Okay, so this was a telepresence robot, and I hope you enjoyed the video. So again, I would like to remind you, so we have three categories of tracking. So the first one is tracking sense organs like eyes, like ears. The second category is tracking human body, so we can track human face, we can track human body itself, right? So as you know, human body consists of some bones and which are joined to each other. So the third category is tracking environment which is around us. So actually the third category looks like maybe one of the complex tracking, because it's very complex. As you know, nature is very complex. Sometimes even if we want to track some for instance, water streams, probably is better to generate them by using specific laws of physics. We can actually also do it in such systems like Blender or Unity. So the next thing, dear students, I would like to talk you today is related to tracking attached bodies. So as you know, many tracking problems involve estimating the motion of the body relative to another, so bodies can be connected to each other. For instance, an eye rotates inside its socket, which is the part of the skull. Although the eye may have 6 degrees of freedom when treated as a rigid body in space, its position and orientation are sufficiently characterized with 2 or 3 parameters once the head pose is given. So if you don't move your head, obviously the number of degrees of freedom will decrease. So other examples include the head relative to the torso and hand relative to the wrist, and the tip of a finger relative to the middle bone. So parts of human body are interconnected to each other. So the entire human body can even be arranged into 3 of attached bodies based on the skeleton. So bodies may be attached in a similar way like other organisms such as dogs or monkeys, and machinery, for instance, such as robots and cars. Actually, human body and those industrial devices, they are having very similar structure if you consider them in terms of bones and joints. So all these things can be called a multi-body system, as I have emphasized it here. So the mathematical characterization of the poses of the bodies relative to each other is called multi-body kinematics, and the full determination of their velocities and acceleration is called multi-body dynamics. So these are the areas of physics which study the mentioned things related to the multi-body systems. So please have a look on the picture which is on the up of the slide. So this mechanism is a multi-body system because it's consisting of different small parts which are attached to each other using various types of joints. So here it's a train, and train also can be considered as a multi-body system because train consists of caps which are attached to each other. So as you see here, so there are some links, or in human body we call them bones, so which are attached to each other using joints. So they are connected in these points. So let's have a look how landing gear, which is a multi-body system, looks like when a plane lands. So when it will land, so you will see that there is an obstacle here. So there will be some changes in the multi-body, this multi-body system. So as you see, there is an obstacle, and so the wheel is still stable because of some moving parts. Actually, they are also used in usual cars, and they organize a suspension system. So please have a look on the next picture. So here I wanted to show you how actually attached bodies can be tracked. First of all, let's have a look at the left picture. So we have two links, B1 and B2, and they are connected using a joint. So which is this is solid point is a joint. So this joint is called a revolute joint, and it will allow one link to rotate with respect to the another. So it can rotate here, it can rotate here until it touches the link. So actually human bones are also working in a very similar way. So we always rotate our hands, knees, and we have some joints. So another type of 2D joint is called a prismatic joint. So here, so this joint allows one link to translate with respect to another. So one link can only move here, it cannot rotate. As in the first case, it could only rotate, but it could not move with respect to the link B1. So two types of joints, revolute joint and prismatic joint. So on this picture, you will see a more complex system, so which is connected with many links here. So the links are connected with joints. So this is, as I mentioned before, so the joint is called revolute joint. So links can move with respect to each other, but they cannot be translated here also. So let's consider some types of 3D joints which actually arise in industry or even in real life. So on the first example, you can see an object with only 1 degree of freedom, because inner circle, which is yellow in color, can rotate only left or right. So no other movements are possible in here. So in the second picture, you will see that a yellow object can rotate inside and outside of the green object. So here again we have only 1 degree of freedom. So the same happens for screw. As you know, when you use a screwdriver, you can rotate screwdriver to the left or to the right only. So we have only 1 degree of freedom. So the next objects are showing higher degrees of freedom, and one of them is cylindrical object. So in here it can be rotated left or right, and also it can move through the hole of the green object. So it has 2 degrees of freedom. So the next object is very interesting. I think you might know where it's actually used in all type of mouses. So this principle was successfully used, and it allowed us to have 3 degrees of freedom, because a sphere which is placed inside this hemisphere of green color, it can roll, yaw, and pitch. So it has also 3 degrees of freedom as the next object. An object which is rigid body, which is moving on the floor, it can move through y and x axis, and it can also rotate. So therefore we have 3 degrees of freedom here also. So now let's have a look on the more complex bodies. So here in these bodies we have 2 fixed points. So this point is fixed and this point is fixed. So therefore, so this object can take only two positions, on this position or this position. So it's constrained because of two fixed points. So the next object is also somehow constrained because it has two fixed points, but here, if you push on here, so the point, this point will move to the left. So it still can take many different forms. So of course, because of two fixed points, it's also somehow limited. So similar things are actually happening in the human body. As you can see, some of our joints are also fixed. For example, a point on the shoulder, so it's not moving much, and so the head is attached to the shoulder, and so these points can easily be moved. So our skeleton also have some constraints. So next we can talk about motion capture systems, and tracking systems for attached bodies use the kinematic constraints to improve their accuracy. So the most common application is tracking the human body, as I mentioned before, for which the skeleton is well understood in terms of links and joints. Such motion capture systems have been an important technology for the movie industry, as the motions of real actors are brought into virtual world for animation. So it was well demonstrated in the first tutorial we have watched today. So please have a look on a human skeleton. So as you might see from here, human skeleton consists of bones, which are called links, and they are connected in connection points, which are called joints. So here they are. So these are connection points. Here the connection point. Here is also connection point. So we have some important points which are also shown on this picture. So with a blue color, with a white color. So these points are the most important points for our bodies when we track them. Of course, more points you have, better you can measure all movements of your human body. So I think it's very important to have a good devices with more points. So in this sense, human skeleton is very similar to some industrial objects like robot arm. So here we also have links similar to the bones, and the links are connected with joints. So this joint, and here also another joint which will move the arm itself. So the structure is very similar. So we use some links and joints here. On the next slide, you can observe hand tracking. Also in the hand tracking, we have some important joints here, and we have some bones, right? As you know, our fingers also contain some small bones which are connected with each other. So we call them joints in virtual reality. So these are green points here. So the more points we have, so more accurately we can measure the movements of human arm, and then we can send this information to a virtual world. So on this picture there is a hand model used by leap motion tracking, and the tracked model superimposed in an image of the actual hands. So it has exactly the same number of points as a real hand. On the next slide, there are some devices which are generally called hand tracking gloves, and so these are gloves, right, with some sensors. As you see here, we have some sensors which track the movements of our fingers. Of course, more sensors you will have, so more accurately you can measure all the movements which are related to your bones. So some of them, like shown in here, they're used for various computer games. So the next thing which we can track is related to our face. So we call these facial expressions. For facial expressions, we need some deep understanding of geometrical modeling, because without geometry processing, so we cannot exactly accomplish this task. So as you see from this slide, so there is a human and there are many points on his face. So these are the most important points. So they can be a little bit less, as shown on some other pictures here. So using those points, we can compute how so the muscles of human face are moving. So then we can send this information to a virtual world generator, to Blender or to Unity, and try to animate facial expressions. So on the next slide, you can see that even there is some other methods which can help us to understand the emotions of a human through facial expressions. So, for example, we can generate some algorithms which will help us to determine if a person's face is neutral, or he's in anger, or he feels disgusting, or he's afraid of something, or he is happy, and many other emotions can be also understood using some spatial algorithms. Of course, all these are related to geometry processing. So on the next slide, I have given you a hyperlink for downloading free track software. Using this software, you can track your head. So first of all, you need to install and select the source, the camera you use. So your image of your face will be given here, and the model will be in here. So when you move your head, it will also move. So your head will be tracked. On the next slide, so there is a small tutorial about Faceshift Studio software. Actually, this software is very good, and unfortunately, it's not a freeware. So here, I would like to demonstrate how it works. Please, attention. Unfortunately, there is no sound, but you can see that the person here tries to show various emotions like happy smile and etc. And the model of his face is shown here, and its rendered case is here. So it exactly repeats all his emotions, and all the facial expressions are very similar to the reality. So I suggest you to have a look on the Faceshift Studio software if you have a time. And then the next thing is another software which is called CrazyTalk. Using CrazyTalk, of course, you cannot do the same as in previous case, but if you have a sound file, or if you can simply tell something, so a person which is a character which can be selected from the software, he can repeat your voice with having some facial expressions and so emotions. So please have a look how I read the poem, and this character will represent it instead of me. Some night and street, some chemist's lantern is bringing senseless very light. Well, nothing changes, that's one pattern. Live extra 25 and find. You die to start a life all over, all things repeat as did before. That night, cold waters at quay border, that light, that street, that chemist's store. So it's very interesting. Some night and street, you can get freeware. Actually, it's not a freeware, but there is a trial version of a CrazyTalk. You can simply Google it and try and install it and check how it works as well. CrazyTalk is very often used by educators who try to develop amazing tutorials as well, especially for children. So, dear students, let's go to the motion capture systems. As you have already seen, on the human body you can find some important points which have to be tracked. So we have to attach spatial sensors to our bodies, and some equipment which track actually the orientation and the position of each point. So we call this system a motion capture system, or you can simply say it a mocap system. So artificial features are placed around the body of a human actor, and the motions are extracted and matched to a kinematical model. Each rigid body in the model has an associated geometric model. As you see for here is the geometric model, which is then rendered to produce the final animated character. So this is the final animated character. So in most of the nowadays animations, so they usually do not animate the movements of characters. Instead, they use sensors for a human body, and a person tries to do some movements which will be after mapped to his geometrical model. So sensors are of course important, and as I said, they're used to build up geometrical models of rigid bodies. It can be any models, like models which can move, or those models which never move, or which are called stationary models. So these models are often built from a 3D scanner with images of the object from many viewpoints in a controlled way. So I think you already experienced it to use a 3D scanner, and you know how it works. So the object may be placed on a turnable which is surrounded by cameras or other sensors, or the sensors may move around while the objects remain stationary. So I'm going to show you some devices which are called SLAM, simultaneous localization mapping. So on the first picture you can see that an object is placed on some black box, and the black box will turn, so the object will rotate, and so SLAM camera will detect and will take the pictures from all its sides. So in the second case, object, there is no object but there is a camera, and if you want to scan something, so you need to move the camera by yourself. So I'm going to show you some of real applications with Visual SLAM. So the first one is just 2 minutes, and this real-time Visual SLAM using only one single camera. So as you see from the video, camera is detecting some objects, and there is some rectangle, and there are some squares which are placed around objects, so we can localize the object, so after we can detect it, of course. So the camera will move, but objects have to be detected. So if they work according to, if the camera works according to some algorithm, of course they should be well detected. On the next example, I would like to show you more complex SLAM. Actually, this SLAM is placed on some moving body like a car, and the SLAM will try to scan the environment. Here is a street, so please have a look. So it's created in Visual Group in Technical University of Munich in Germany. So first, this camera is moving inside some room, so it can understand the depth of the images it takes. So that's why a 3D model can be built up, because this is a 3D scanner. On the second example, as you see here, car is moving along some street, And SLAM camera takes videos of everything it can see, and then a 3D model can be generated from those videos, because SLAM cameras, they can understand the depth of the image, so they can understand the distance from the camera to any object it can see. So using such SLAM cameras, we can easily scan the environment which is around us. So we can generate large models of cities, streets, and buildings as well. This is how it works. As you know, in virtual reality, it's not easy to create 3D objects, especially in some software like Blender, so which is based on mesh modeling. So therefore, some objects can be easily scanned, and I think you already know how to do it. Alright, so thank you for your attention, and have a good day.